Right, and the other group, by the way, do you have a project? Or
Figuring it out. Our third person's sick, so he's not here today. He finally answered me today.
All right.
Can I email you by the end of the day?
Oh
Is
yeah,
that
sure.
okay?
It's kind of want to know what everybody.
Yeah.
All right. So let's start by discussing our logic puzzles to get the ball rolling. So last time we had a variation on the portrait problem. So what do you think is the solution to this problem?
His father,
Why is that?
because he has no brothers or sisters, so his father's son would be him, and the person that he's looking at, their son is him, so it's his father.
Okay, everybody with us? All right, we can apply the same logical substitution trick that we had before. Whenever you see my father's son, that basically means him, because he has no other siblings. So this man's son is me, which means it's his father, right? Okay? All right, hope you all had fun with those. All right, so now today's puzzle of the day, here it is. Enjoy your couple of minutes of thought, and we'll move on. So, are we ready to move along? Okay, so we'll talk about it next class. Okay, so last time we discussed the binomial distribution, right? And as you might recall, the basic idea is we can determine easily the probability of any individual specific sequence of outcomes that might occur, right? Which is, since each outcome in the sequence is independent, the probability of a sequence of outcome is just the product of those non-conditional probabilities, right? So then the problem becomes simply a problem of counting, right? If we want to find the probability of getting, say, 10 wins out of 100, it's simply a problem of counting how many unique sequences of wins and losses are going to have 10 wins in them, right? And we discussed sort of a general purpose method of counting these sequences. We talked about permutations and combinations, as you may recall, right? So hypothetically, we should be able to easily determine the probability of any of these points on the graph by simply counting how many unique sequences of wins and losses produce that many wins, right? And then multiplying that number of sequences by the probability of any particular sequence of wins and losses, right? So, we kind of ran out of time last time at this point. So let's just make sure we recall the stuff that we talked about. And let me ask you to take a couple of minutes and find me the number of ways we can achieve, say, 4 wins out of the 100 losses. Raise your hand if you are done. And raise your hand if you're still working on it. Imagine if this were a pop quiz. And how would you do? That's not good. And then when you're done, you can actually use the vector of, you can multiply the number. I remember that we want to find the number of means equal to that, regardless of which order we take the definition of the number. Right, so we're looking for combinations, not permutations. Oh, so you're finding the probability. What is the number? I mean, I don't know, what was your, what was your answer? Not too lazy. Right. On that?
I found the number of
And then that, does this represent 100? So that's why I would have really.
How many ways can you arrange?
Yeah, why do you have
And get that?
Oh,
If we go in like this, then it's just the whole process.
How much work? It's not hard, right? Although I appreciate your.
This is
So when you find, you're just picking positions for the
place of this.
right? The rearrangement of positions counts as a different, right? So we pick a win in position 1 and then another win in position 2.
I get that.
It counts as a different thing as when we do the permutation, right? As when we pick a position, win in position 2 and a win in position 1. Right? So we want, with combinations, we can divide out all the clones, right? You can have a bunch of clones, like win in one position 1, position 2. Counts as different
I know what
sequences
that
win in
is.
position
That
2 and
is
position 1.
4 times.
Even though they're the same.
The 100 plus one is
Right, so the combination is the one where we take out
it's
and
like
we say
how
this
much
one groups
Yeah.
of
and
positions,
then
and
there's
we don't care
100
which
total.
order they come, right?
So we can have it.
But if you think about it.
So in the combination, we have divided out the clones and we just take the.
No, I get it.
That's
Isn't that,
And
isn't that from
the 100 different colors, and I chose purple.
No, permutation is where order matters, but for us, order doesn't matter. The order of picking where the winds go, not the position of the winds, right?
I have both.
So let's say we have a, okay, so let's say we have a, a sequence of 100 losses, right? And so one possible sequence is about 4 wins in the first 4 positions, right?
Yeah,
That's
they-
one sequence. How can we specify
I
that
couldn't
sequence?
watch it.
We could say, well, we win in position 1, win in position 2, win in position
The idea.
3, win in 4.
It
Another
was
way
like
to
he
specify
drove
the
her
sequence
to
is to say,
madness,
well, we win in
then she
position
would
4,
burn herself
and we
out.
also win in position 3,
Oh my
and
God.
also win in position 2, and also win in position 1.
Yeah.
It's the same sequence, we're just describing it in different
That
orders.
show that you,
Right.
the lab leader shows.
So
you
when we do
Oh,
the partial factorial of 100 times 99 times 98, etc., we are doing that, right? We're just picking where
okay.
to
Steven
place the
Drew,
wins. And
those
order
drinking
matters,
pretzels.
right?
Like $15.
When we do that. And we can talk about
I told him not to
probably
play.
we're not doing it. Right? So then we need to take out the number of permutations within each combination, right?
I'm sorry.
Last night waiting.
You buying that?
They sold out right in front of me.
And so here you have already found the number of permutations, right? Which is the number of ways we can specify some particular sequence. right? So we're saying like where can I place the first one? It can go in any one of 100 positions, right? So I have 100 possibilities.
See, the most common possibility
And then you say for each one of those, how many ways can I play the second one? Well, one of the positions is already taken, so you have 99 positions to play for the second one. And then for each one of those, 100 times 99 is where can I place the third one? And
don't
you
get
have
like
98
my
positions
thought
to place
process,
the
like
third
if I were going to try
right?
and
And
figure
so on.
this
That's
out,
why
I
we
would
get
not
this
multiply
for the
by
number of
that.
possible permutations of where we can place the wings.
I don't get
Right?
the formula.
Now, when we do that, remember we say like for each one
I know,
of these,
I know.
right?
I like
Right?
how I understand that is it's completely explained by everybody. Like, why does this work?
But like if
This
we
is
pick,
because
pick the first
that.
one to be in position 1 and pick the second one to be in position 2, counts as one possible bit. So if we pick the first one to be in position 2 and the second one to be in position 1, that counts as another possible bit. But we don't want that, right? So that's why we need to divide out the number of clones, right? Which is, well, how many different ways can you rearrange 4 numbers in the group?
Well, should we make it 10, something
Yes,
like that?
right? Not just 4, right? Yes. And that will give you the number of unique sequences that are actually. So you have plenty of multiplication going on here. Is that enough for you? Oh, I mean, that is when you want to find the probability of that happening. Which is, I asked how many number of sequences that produce that happen. So we don't want that yet. Now, if I were to ask them what is the probability of happening, you would take this number times the probability of each possibility that we produce it. Okay? All right, so now let's go back to our discussion last time. So what is the number of sequences that we produce for widths? About 3.9 million, right? So if we did it correctly, we should have 3.9 million sequences of the widths, right? Now, how do we find that, right? First, we're saying I need to fill 4 bins with positions where a wing can occur, right? So there's 100 possibilities to place the first one, and for each one of those, we have 99 places remaining for the second one. And for each one of these, there's 98 for the third and 97 for the fourth, right? So that here is 100 factorial over 96 factorial. But we don't actually want to calculate the factorial, right? So we cancel that in our mind and then the tip of the factorial, right? And then we say, okay, well, we don't want to count the permutations of the different positions, right? Because, a sequence that is specified as a wing position 1, 2, 3, and 4 is the same sequence as if we specified it in position 4, 3, 2, 1, right? Because then there's a different way of specifying exactly the same sequence of wings and losses, right? So we want to take, want to factor out all of the clones of a single individual sequence of wings and losses. So we have a question of how many different ways can we rearrange 4 positions? And what is the answer to that? 4 factorial, right? Which happens to be what? 24. Okay. So now we say, okay, we have this number, which is the number of permutations of the 4 positions where the wings can be placed. But, for each unique group of positions, there are 24 ways to specify it. So we're going to divide out by 24 to produce the actual number of unique combinations, which is now 3.9 million or so. Right? Now let me just ask again, is the logic of this clear to everybody? And do you understand why, when we do the top bit, we're not counting the combinations, why we're counting permutations?
sorry, we're,
Can you repeat the question?
yeah.
Do you understand why when we do this top bit, which is this bit, right, n over n minus k, that's what it is, right? Why we're counting permutations and not combinations? Right? So why is that? You say yes. You have to explain how what your understanding is.
Because that's in the formula. Because you have, you want 4 positions because you want to win 4 times, and you have 100 possibilities for each one, and order does matter for that part.
So you're right, it does matter, but why is it that by construction order ends up being mattering? Right? Why is that construction producing permutations and not combinations?
Because, I don't know if I can explain this well, but the first time, for the first position, you have 100 choices or positions where to choose that win from, and then after you take that win, there are only 99 other places that you can choose it from. I don't know how to explain it well.
All right. Well, so let me give it a try and see if you will buy that. All right. So when we're doing that, right, we're filling our 4 bins, right? Let's just imagine something much smaller number, so we don't have to think that large and all of that stuff. Right. So let's imagine that we're picking 2 numbers out of 10, right? And you're saying like how many different ways can you pick 2 numbers out of 10? And so I say, okay, so in the first position I have 10 possibilities, in the second position I have 9 possibilities. Each one I have only 9 numbers. Right? Now let's think of this in terms of the decision tree that we're producing, right? So we're saying that in the first position we have 10 possibilities. Time of 5, right? The thing we're picking 2 numbers out of 5. Okay, so then we have 5 possibilities, right? So out of our starting point, we have 5 possibilities. We can pick 1, 2, 3, 4, 5, right? And then we're saying for each one of these, how many possibilities do you have to pick the second one? Well, there's 4. So if we pick 1, we can pick 2, 3, 4, 5, right? If we pick 2, we can pick 1, 3, 4, 5. We pick 3, and so on and so forth, right? But now notice what's happening, right? In this branch of the decision tree, we had a pick of 1 and a 2. In this branch of the decision tree, we had a pick of a 2 and a 1. Right? So you can see that we're reducing the clone where the order is mattering by essentially replicating our decision tree here, right? You can see that we're going to reduce each possible sequence of picks. Right? We're not counting new groups, we're counting actual sequences of picks. Right? So if we want to figure out what is the unique number of groups we can pick out of 5 numbers, if we're picking a pair of 2, right? We would have to divide by 2 because each one is replicated twice. Right? It's making sense? Everybody? Yes?
What do you mean by producing clones of clones?
Right, so if we're saying we're picking a 1 and a 2, that is a clone of a 2 and a 1. Namely, if we're counting the unique groups of numbers,
Okay.
right? This is the same group, but we're counting it twice, right? So they're clones of the same group,
Okay.
right? That's what it means. Okay? Attack of the clones. Okay, so the same logic applies if we're picking 4 out of 100, right? When we do this, how many, for each one of these, how many of these, and how many of those, right? We are picking individual, where order matters, right? The different permutations of how we pick are all counted in here, right? Because sometimes we start with position 1, sometimes the same position is over here in position, right? Then it's still position 1, right? So that's why. Right, just on a sort of, by construction of the method of how we're counting the picks, right, we're counting permutations, which basically multi-counts if there are a group of choices. Right? Okay? All right. So you can see that, this is of course equivalent to n factorial, that. N factorial n minus k factorial, which is the numerator, right? And then k factorial, 4 factorial, right? And again, if some of you tried to put 100 factorial into your calculator, you probably got an overflow error because 100 factorial is really, 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 really large, right? Okay? All right. So take a guess, right? Let's take a look at this point right here at the tip, right? Oh, wait, before we do that, right? So we have 3.9 million ways to pick 4 wins out of 100. And each one of those ways can occur with probability 7e minus 31, right? You remember that? Right? The probability of each individual sequence of outcomes is 1/2 to the 100, right? So we get 7e minus 31. And so we can have 3.9 million ways to land on one of those. So the probability of getting 4 wins in goal is 3.9 million times the probability of each one of those happening. Yeah.
What's the probability number?
It's 1/2 to the 100, right? Comes out to 70 minus 31 or so. Right? So it's like if I were to ask, what is the probability of landing on a 1 or a 2 if you throw a regular 6-sided die? What would that probability be? 1/3, also known as 2/6, right? Because we say that 1 and 2 are mutually exclusive outcomes. Each one has a probability of 1/6, and we have 2 of those possible outcomes that will produce what we want. So the probability is 2 times the probability of each one, right? The same thing here. It's like we're throwing a 7e31 sided die, and we're denoting some of the sides as the outcome that we want. And then we're asking what is the probability of landing on one of those sides, right? Everybody with me? Any questions? Okay, so now let us observe this graph, and let me point this point at the tip here, and give me a rough ballpark estimate of what is the number of sequences that will produce 50 wins out of 100 tosses. That means, by a rough ballpark estimate, I mean, you do not actually have to calculate, partial factorial of 100 down to 50 to do this, right? Just look at that and think if you can come up with a rough ballpark estimate of what would be the number of sequences that produces 50 out of 100. By roughly, plus or minus an order of magnitude, I'd say. And while you're thinking, I'll be right back.
Then in 50. So you have 100 and then in 50. And that's your percent chance of winning. So. Is it? You do 100.
Anyone have an estimate of the number of ways we can produce 50 out of 100 wins?
Is
Yes.
it like 1.2 times 10 to the 29 or something?
Why is that?
Well, because that probability is like almost 10%. So if you take 10% of like 2 to the 100th, which is the probability of like everything happening, you're gonna get like the 50-50 chance.
All right. Plus 2 Wolkenstein points for you, my friend. All right, so here's the deal, right? The probability of this event happening is about 8%, right? You can see that, right? This is the probability of this, right? Yes? So, how many sequences must we have in order to produce an 8% probability if each one of those sequences is 7.8 e minus 31, right? So basically we go from 8 e minus 31 or so to 8 e minus 2. What do we need to multiply by? 1 e 29 or so, right? OMG. I know, I'm like, let me write it out on the board, right? So here's the thing, right? The probability of one sequence is 7.8 e minus 31, right? Which is, approximately 8 e minus 31. Okay? Each one, any individual sequence has that probability of randomly happening. Yes? Okay, now we're saying we have some kind of a compound event composed of many of these sequences that produces a total probability of 8%, which is 8 e minus 2, 0.08, right? 8 e minus 2. Alright, so what we're saying is, some number of sequences x, which we don't know, times the probability of each sequence, 8 e minus 31, produces a cumulative probability of 8 e minus 2. Right? Everybody with me? It's cool? Okay. Better? Okay. Sorry, I threw it all out there, but thanks for asking me the question. So now we need to figure out what is this x, the number of sequences that we multiply by 80 minus 31 will produce 80 minus 2. Right? Well, in order to cancel that, minus 29 out of 80 minus 31 has to be something times 10 to the 29, right? Right, because 8 e minus 31 basically is 0 point followed by 30 zeros and 8. So how big of a number do we need to multiply by in order to get 0.08? Well, we need to cancel out all of these decimal points, right? So we can multiply by about 1e29 to cancel out 29 of these zeros. Okay. Right, so we go from 31 to 2, it's 29, or is it 92? You mean this one here? Right, so x is our unknown number of sequences. Right, the probability of each sequence is about 80 minus 31. And the total probability of that event of getting 50 wins out of 100 is 8%, which is 80 minus 2.
So we just do like the 8 divided by 8.
Exactly. Right? So to solve for x, we'll divide both sides by 80 minus 31, we get 80 minus 2, or 80 minus 31, and we'll end up with 1 e 29. Right? Any questions? We buying that? Right, so to go from almost negligible probability of 80 minus 31 to get to about 8%, which is like a measurable real probability, right? We know that there must be a really, really huge number of sequences that will produce the remaining one, right? Otherwise, there's no way we would get a reasonable probability that it happens. Okay? So are we buying that? And does anyone have any questions? Okay, good stuff. Right, but so you can see that this probability distribution is also a distribution of how many ways we can produce that particular answer. Right. So as we get closer and closer to about half of the 100 trials, right, we get more and more ways we can rearrange the wins in different positions. Right? So we have the greatest number of ways right here in the middle at 50, and it kind of falls off as we get further and further away. And once we get out to the tails, we have relatively very few unique sequences that produce some particular number of wins. You have a question?
Yeah, how do you get the 8 into
Well, 0.08, right, is 8 divided by 100. Right? So 100 is 10 to the second. So something divided by 10 to the second is multiplied by 10 to the minus second.
Well, isn't E like 2.0
Oh, this is scientific notation. We're not talking about E, the natural, the base of the natural log guy, not the 2 point whatever. Right? It's just, scientific notation when we write something like x e y, that just means x times 10 to the y, right? So it's just a shorthand for writing the times 10 to the something. Yep.
I think 8%.
What do you mean, like?
I was on the graph, and how did you get that? For this, and how did you get 8%? You have to know how many times it's possible to get 50.
Oh yeah, I mean, this graph was generated by R, which is a statistical and programming software package that can basically has native code to deal with a bunch of distributions. So I didn't actually count the number of ways for each point. I just basically wrote a little command that says, plot me the probability of each outcome for a binomial with 100 trials. And bam. But yes, I mean, if I were to do it by hand, I would have to calculate some really big numbers. Now, there are actually some fancy pants mathematical shortcuts for calculating pretty good approximations to factorials, right? Because, obviously, actually calculating the factorial is a really difficult task. The numbers get really, really large, right? But there are, mathematical approximations that we can get to calculate the order of magnitude of the factorial pretty quickly without actually having to multiply a bunch of integers, right? So my guess is, without actually looking at the code for how they wrote this, since it took approximately 0 seconds for me to generate this graph, 0 seconds of runtime, my guess is they're not actually multiplying integers, they're probably using some kind of a rough approximation for this factorial, right? But yeah, I can't actually tell you what algorithm they use to find this, to find the number of sequences because I haven't actually looked at the code. And actually, I could probably look at the documentation and they'll also tell me what algorithm they use to approximate. I haven't done that. That's a good question, though, right? You're thinking, how could we come up with 829 items? You would have to multiply really large, right? Which, thankfully, I did not. All right. Any other questions? Okay. All right. So the probability of any particular sequence of outcomes happening is very, very small, right? Like 7 or 8 to minus 31. And we discussed how, it's just basically almost just about impossible for you to just randomly pick some particular outcome and then do this exercise and come out with that exact outcome, right? But here's the thing. If you take a coin and throw it 100 times, one of those outcomes will actually occur. Right? It has a probability of happening of 7, 8, e minus 31. And there's a negative, but it actually will occur. And one of them has to happen. Right? Blows your mind, doesn't it? An impossible event just occurred. Right? So the problem is not the fact that one of them will occur. The problem is picking it in advance. Right? That is really the impossible task. But one of them will have to occur, right? You throw a coin 100 times, it will happen. One of those sequences of outcomes will happen. Unless, as you're throwing the coin, somebody runs in and steals your coin. Complete the experiment. Right? Okay? Any other questions? Are we buying this framework, the idea, the distribution? Does it make sense to you? Okay. So let me point out some salient probabilities of things that might occur, just to give you some more gut feeling of how things are falling out. And so we already talked about getting 100 losses, also known as 0 wins, is about 7.8 e minus 31, really small. Getting 99 losses, aka 1 win. We have 100 ways of producing 1 win out of 100 losses, right? Have a win in the first position, second position, etc., all the way up to the 100th position. Right, just 100 ways. So obviously 99 or 100 losses is the sum of those two. Now, remember how many ways we can produce 2 wins out of 100? I believe we calculated that last time.
Was it 4,950?
There's 4950 ways to pick 2 out of 100. Now, and then to pick, alright, so then to pick 4 out of 100, we just calculated it to be 3.9 million. Alright, so you can see that this number of ways to pick something grows really pretty fast, right, as you get away from the edge. Right, you can start from 0, 100, 4950, and then right we're out to 3.9 million, and eventually as we're in the middle, we get to 129 or so, right? So it's just the magic of factorials and combinations and all that. So hope you have some kind of an intuitive feeling for how these things are working out as you change conditions, right? So now we have one probability here, 67 or more losses. Now why did they pick 67, do you think? Why is that number important to us in the statement of our particular problem? Yeah, so why is 2/3 important? Yeah. Right? Exactly, very nice. +1 Folkestone point. Right? Remember that our original problem was you lose 100 with a 50% chance and you gain 200 with another 50% chance. So 67 or more losses will produce a net loss for you after the throwing of 100 coins. Or throwing a coin 100 times. You don't actually have to use it. Right? So 67 or more, the probability of 67 or more losses is the same thing as saying the probability of losing money on this exercise. Right? And that is, of course, just on a sort of intuitive level, kind of an interesting probability to know, right? If I take you up on this offer, what is the chance that I will lose some money? As it happens, you can see that it's not astronomically small, but it is pretty small. Right? We have 4/100th% chance of losing any money at all if you decide to engage in this 100-point loss 2-to-1 game. Right? which is not so bad, right? You can, 0.04% chance of losing anything. It's pretty good odds, right? So now remember, what was the probability of losing anything if you play the game just once? If you just play one round of a coin toss game, what's the probability of losing it? What's that? It's 1 out of 2, which is 50%, right? Now, if we increase the number of tosses to 100, we get down to 0.04%. All right, so to give you some more representative numbers here, right, the probability of losing anything on one toss we have is 1/2. Now, if we aggregate this to 10 tosses, the probability of losing anything is 17%. Significantly less than 50%, I must tell. Right? Not really very, very small, but it's a significant reduction. If we go from 1 to as small as 10 repetitions, we have already reduced our chances of loss significantly. All right? So how many losses must we have out of 10 in order to lose money at the end of the day?
Is it 7 or more? Or 6
7 or more, right? So if we have 7 or more losses out of 10, we will, in the net, we'll lose money. Right? If we have 6 or less, we will have gained some amount of money, right? And remember, this is, this is a 2-to-1 game, so essentially it's a 1/3 to 2/3 ratio of wins to losses to get to the 0 points approximately, right? Now you can see that as we go up to 30 repetitions, we're down to 2%. 100, we're down to 0.04%. 1,000, we're starting to get into the microscopically small probabilities that basically mean don't count on ever losing money on 1,000 repetitions, right? Okay, so now, the point of all this is, number one, I could have just said, if you do something, do a bunch of independent trials a lot of times, and you have a net positive expected value, you're not likely to lose. But that's not, that statement by itself wouldn't really have meant a whole lot to you, to understand what's going on with the probability, why it's occurring, what is the actual relationship between, the number of repetitions and the probability, all that kind of stuff, right? So I really wanted you to understand the background, the basic math and the basic probability that goes into, repeated trial experiments. That's what kind of life is, right? A repeated trial experiment. Yeah.
Can you give me some
Well, so here we have, okay, that's easy, right? So we have 10 repetitions, right? So we say, what is the probability of 7 or more losses, which means 3 or less wins, right? Because in order to have a net loss, and we're playing a game of 100 to 200, 2-to-1, right? You can say, right? You can say, okay, what happens if I win 3 times and lose 7 times? Well, my net take is going to be 3 times 200, which is 600 on the wins, and my loss is going to be 7 times 100, which is minus 700 on the losses. So I have lost money. All right, so if you have just one more win, if you have 4 wins and 6 losses, you will be already making money in the net, right? So 4 times 200 is 800, and 6 times minus 100 is minus 600, you made money. So in order to figure out what is the probability of loss, you need to figure out what is the probability of having 0, 1, 2, or 3 wins out of 10. Right? So in order to figure that out, we go back to our basics of the binomial distribution. We say, okay, first of all, what is the probability of having 0 wins out of 10 tosses? How do you find that out? You don't have to actually calculate it. How do you find the probability of 0 wins out of 10 coin tosses? Exactly, right? 1/2 to the 10. whatever that happens to, whatever that turns out to be, right? It'll be about 1 out of 1024, just to the 10th is 1024. I'm sure right, so it'll be about, 1 out of 1,000 chance of having all losses. Then you say, what is the probability of having 1 win out of 10 losses? Well, first of all, they say, how many ways can I produce 1 win out of 10 losses? How many is that? 10, right? You can have a win in position 1, win in position 2, 3, or all the way out to 10, right? There are 10 possible ways to win only once out of 10. Right? And the probability of each one of those occurring is 1 out of 1/2 to the 10. So the probability of having 1 out of 10 wins is 1/2 to the 10 times 10. Right? And so on and so forth, right? We can replicate what we did with 100 tosses for any number of any number of samples, right? So that, of course, it's kind of tedious to actually do that by hand for all of these, right? That's why we have software that can help us out with this stuff, which is what I use. Right? I don't think I actually calculated these by hand for each one, but you can always double check what software is doing by clicking through simple cases and seeing if it produces the correct result.
So what was the vision for the second?
You mean for this one?
Yeah.
All right. Well, the probability of getting some loss out of 10. That's 3x in both space. Probability of getting something like getting a loss out of 10 is the probability of getting 0 wins plus the probability of getting 1 win plus the probability of getting 2 wins plus the probability of getting 3 wins. Right? So you calculate the probability of 0 wins. That's 1/2 to the 10th. Calculate the probability of getting 1 win. That's 1/2 to the 10th times 10. Right? Then you calculate the probability of getting 2 wins. 1/2 to the 10th times however many ways you can pick 2 out of 10. Right? That's going to be 10 times 9. 35. Right? So 35 times 1. And then there was the probability of getting 3 wins. Right? That would be again 1/2 to the 10th times the number of ways we can produce 3 wins. So that would be 10 times 9 times 8 divided by 6. Right? Yes? What does that come out to be? That would be 10 times 3 times 4. So that would be 120. Yes? Right? So that would be 120 divided by 2. And we add them all up and find the probability of having a net loss out of 2. And assuming you did everything correctly, you should find that all of this adds up to 17.1875%. Right? Is this making sense? Everybody that? Okay. And so, we can do the same thing for the probability of a net loss after 30 tosses, right? So what is the maximum number of wins we can have out of 30 and still lose money? Or not win. Right, it'd be 1/3, 1/3 of all the tosses, right? So now here we're looking to find the probability of 10 wins or less, to find the probability of 0 wins, 1, 2, 3, 4, after 10, and add them up. Right? Okay? Any questions?
Did you get those numbers by integrating under curve? So like for P loss 100, if you start at 67 and you just integrate under that, are you going to get the
Yeah,
same?
that's, I mean, effectively what we're doing is like discrete integration, also known as summation, right?
Yeah.
Remember that the integral sign stands for summa, which is sum, right? So, and this is this is not a continuous distribution, it's a discrete distribution. For a continuous distribution, we would in fact actually integrate the area under the distribution, right? It's a discrete distribution, so we're just summing them, but that is the discrete equivalent of integration, right?
Yeah.
But I didn't want to actually get into this continuous distribution. It's not really adding that much to the point of the discussion. But I'm glad you're thinking about it. All right, any other questions or comments? Okay, right, so, the point of all this was to demonstrate and to really give you some sort of a gut feeling and mathematical understanding for how event aggregations work, right? Because in life, life is an aggregation of a bunch of events. And ideally, the point of this exercise is to get you to think in the wide framing for any events that you might encounter in your life, right? If you encounter, in your life, you encounter events one by one, right? Something happens today, some opportunity comes along tomorrow, right? So they happen one by one. But in the aggregate, if you think about it, you know that in your lifetime you'll have many, many different events happening, right? Hopefully. So you want to take a broad framing view of this and make the decision that will maximize your expected value in the long term, right? Maximize your utility in the long term, right? Because if you bypass all risky opportunities because, hey, it's kind of risky and I'm risk averse, and you don't think about the fact that over time, these different dependence events are going to aggregate and the law of large numbers will take hold, right? You are basically cheating yourself out of all this utility you could have had out there, right? You don't want to do that. Utility is good, right? We want to end up, at the end of the game, we want to be sitting in a big pile of utility and smiling, right? Or something to that effect. So that's, so the point is for you, to realize and really internalize, understand how this actually works, right? That the probability of as you aggregate more and more independent outcomes, as long as they all have a positive expected value, the probability of getting a net loss from that gets really, really small, right? Maybe not as fast as it gets in our example, because getting 2-to-1 odds on things is relatively rare, right? But still, it gets small pretty fast as you get into the hundreds and thousands of different events that will occur in your life, right? So I hope this was a sort of an educational exercise to delve into the basics of probability and statistics so that you can understand how things work. If not, then at the very least, I hope you take away the moral of the story, so to speak, that you should take the broad framing view of your decisions rather than focusing on each one individually and not thinking about how it fits into the rest of your life, right? So now, obviously, in real life, nobody is going to walk up to you and offer you a 2-to-1 game of heads or tails, right? Because if they do, they're either really stupid or they have a trick coin and it always lands in their favor or something, right? So I want you to, in the spirit of our earlier discussion of going from the general to the particular, I want you to think of some examples of positive expected value propositions you might encounter in your life, right? Again, if we're talking about coin tosses, you say, well, yeah, whatever, it doesn't really happen. It doesn't apply to anything. Right? So I want you to think and come up with some positive expected value propositions you might actually encounter there. Do you happen to have an idea for what might be a good example? Let me know. Where do you got it? Yeah. Okay, how is that? All right, that's that's a good example from the financial industry, right? You might think, I have this extra $1,000 sitting there, and I don't anticipate really needing it for anything in the shorter term. What am I going to do with it, right? Well, I'm sort of risk averse, so maybe I'll just park it in my bank savings account and let it sit there. At least I'll know that it will remain $1,000, and it's not going to go down. But if you look at the statistical properties of financial asset returns, you will see that on average, number one, that on average over time, say a portfolio of equities has a positive rate of return of approximately 8 to 10% historically, right? So if you can afford to let that $1,000 sit for a while and you don't need it, then you're going to be aggregating a number of independent return events over time, right? What's the return this month? What's the return next month? The return next month, right? So you're going to be aggregating a number of independent events, each of which has a positive expected value, right? So if you think of each month in separately, you'll say, well, if I put it in the portfolio of equities this month, it might go down, and it would really suck, right? And it would. Right? So maybe I better leave it in my bank account. And then next month comes along and you say the same thing. Well, if it goes down, it really sucks. Maybe I better leave it in my bank account. And so on and so forth. But if you take the broad frame view of the whole timeline of investment, you will realize that you will be better off taking the riskier choice and investing in maybe an equity portfolio which has a positive expected rate of return and positive expected value over time, rather than leaving it in a bank account, which actually has negative expected value due to inflation, which we will talk about at some point in the future, possibly very soon. Right? So, if you think about it, how many, if you know, what is approximately the interest rate you might get in like a Wells Fargo savings account? Yeah.
0.1%.
Something to that effect, 0.05 to 0.1% interest rate on your Wells Fargo savings account. Right, so if you leave like $1,000 in your Wells Fargo savings account and you get 0.1% interest rate, what will you get at the end of the year? Well, approximately nothing, but what will it be exactly? $1, right? Which is nothing, like a big amount, or a small amount. Yeah, one of the right. So, but guess what? In the meantime, what is the sort of the average rate of inflation in the recent years? Closer, actually, the Fed targets like 2 to 3%, 4% really on the high side, 2 to 3%. So think about it. If you just leave your money sitting there, at the end of the year, you lose 2 to 3% of the purchasing power of your money, right? So at the end of the year, you started with 1,000, you lose 3% purchasing power, then you end up with purchasing power of $970, right? So you gain $1 in interest on your savings account, and you lose $20 to $30 of purchasing power at the same time. So in effect, leaving your money sitting and earning an interest rate that is less than the rate of inflation, you have a negative expected value of return as measured in terms of real purchasing power. You don't really want to be in the habit of doing that very much, right? Now, there is something to be said for having, certain liquid cash reserves for emergencies and whatever, right? You don't want to have absolutely no liquid cash sitting anywhere at all. Right? But you don't want to have so much extra cash sitting in your bank account that is just sitting there and losing purchasing power. Right? So that's why in our example I said, assume you have like an extra $1,000 you don't anticipate needing. You already have whatever liquidity reserves that you need. This is like an extra $1,000, right? So how about anybody else? Do you have any examples of positive expected value propositions you might encounter? You have 3 minutes to come up with some positive expected value propositions. Oh yeah, sure. Not before you give me an example. Anybody? Hmm? Well, that's an investment, right? So, yeah, you can do a historical return with gold. But at least you might expect that it will save you from losing the inflation, right? Because that doesn't really build up in there, right? But it goes into the investment bin. Anybody else? Now, how many of you have bought stuff, like some kind of equipment in a store, and then at checkout you were offered an extended warranty? Right? You're familiar with that concept, right? Even if you haven't actually bought stuff, right? So, now take a guess, without doing the background research required to actually estimate the probability and severity of losses in some particular time period, which some of you will probably do for your research project or some aspect of the insurance industry. Take a guess. Do you think it is a positive expected value proposition that is being offered to you when you're being offered an extended warranty?
If you plan on breaking it, yes.
Well, assuming you do not deliberately plan on actually just like breaking the stuff, right? I mean, of course, there's the whole moral hazard problem with insurance, is that, people who take out insurance might be the ones who plan on like breaking stuff or like killing themselves if we're talking about life insurance, right? Or whatever, right? Assume that we're not talking about you being like deliberately trying to scam the insurance company, but just you're going to use your stuff and whatever happens, happens.
All depends on what the stuff is.
Well, here's the thing. Let me give you a hint. The answer is no. It is not a positive expected value proposition, because if it was, they wouldn't be selling it to you. The whole point of insurance is to price risk above its fair value so that on average the insurance company can make money, right? So you know that on average they're not going to sell you a protection from risk below the expected value of the risk, which means that buying insurance in terms of expected value is always a negative expected value proposition. Now, that doesn't mean that you shouldn't buy insurance for large losses that you cannot swallow yourself. That's the whole point of the insurance industry. But, as we'll discuss next time, because I can see that we're out of time, you do not want to pay money to insure against small losses which you can swallow yourself, because in the aggregate over the long term, you are likely to be losing money. With possibly certain exceptions like window insurance that you mentioned before, right? Okay, so next time I want you to think about more examples of positive expected value games, and we'll start with that discussion. Then we'll talk about making financial plans, and we'll discuss your financial plans, which hopefully by now you have made, because it was done from a week or two ago. And then we'll